We'll start up with the first topic, that is problem solving, search and control. In this chapter, we'll be starting up with recall of the algebraic functions. Now, a function may take any of these forms. The first form is that of the ordered pair, or it can be a graph, or it can be an equation. There are certain conditions that are to be satisfied for a function. That means no two ordered pair may have the same first member with different second member. Now, even before we talk about this, let's know about what is an ordered pair. I hope all of you might have certain amount of idea about the ordered pairs. In case of ordered pair, we are having two characters, that is x and y. The first one is called as the first member, the second one is called as the second member, right? When there are multiple ordered pairs, we call it as a relation. Let's say we are having xy, x2, y2, x3, y3, xn, yn. Then this whole part is called as the relation. So what we can see out here is that a relation can have multiple ordered pairs kept together. Now, whenever we are having a relation, it doesn't means that if there are multiple ordered pairs that are present in a relation, it doesn't make it a function, right? Now let us know about what is a function. Function is something where no two ordered pairs have the same x value, but may have same or different y values. Now let us see with an example. Let's say there are two relations. One is f, another one is g. They are generally denoted by lowercase. Now here, for example, in 1 we are having f, and in case of 2 we are having g. In f, all the x values of the ordered pairs are different, and the y values are also different. The y values could have been same also. Now, generally what we are going to see here is, in case of f, we are having three ordered pairs. The three ordered pairs are 2, 3, 0, 0, 6, 4. In these ordered pairs that are present in f, the first element 2 is x, the second element y is 3, and in case of the second order pair, the first element, that is x is 0, y is 0. In case of the next one, x is 6 and y is 4. In case of g, it is the first one is 3, the second one is 1. In the second order pair of g, that means in 2, we are having x is 3 and y is 6. Fine. Now, in case of f, we can clearly see that we are having different x values. That means here x is 2, x is 0, and x is 6. Now, since we are having different x values in case of f, and we are not going to see whether we are having same y values or different y values in case of 1, that means in case of f, so we can say that f is a function. Whereas in case of g, we are having the same x values. The x value is 3 out here, and the x value is again 3 out here in the second order pair, whereas the y value is 1 and the y value is 6. In case of 2, we can observe another thing which I have written out here. That means the x values are same, and hence will not have to check for the y values. Here in this case, we are not even checking for the y values. Since the x values are same, at that very moment itself we can discard this from the list of the functions. So considering the above two relations in 1 as well as in 2, f is a function whereas g is not. Now we'll see the definition of domain. In case of domain, at first the relation has to be a function. Now the definition of domain starts with, generally in the books the definition is somewhat a little more complicated. Now in case of domain, at first the relation has to be a function. That means first it has to be a relation. That means it must comprise of a few ordered pairs. When it is having a few ordered pairs, we need to see whether it is a function or not. The moment we are talking about whether it is a function or not, we need to go back and check for the definition of the function. That means no two ordered pairs have the same x value but may have the same or different y values, right? So when we are satisfying these two conditions, then the relation is a function, and the set of all the first members, when it is already a relation and the relation is a function, then we need to check that the set of all the first members of the ordered list is the domain. For example, in f we are having a, b, b, c, c, where a, b and c, that means I am talking about the small a, small b and small c, they are all different in case of f. whereas they are having same y values in the form of capital A, capital B, capital C, or different y values. We just need to check whether they are having a different x values or not. Yes, we are having the different x values. So in this case, the domain is nothing but small a, b, and c. The domain of this function f is nothing but a, b, and c. Now, since we have talked about the domain, let's talk about the range. Now, like the domain, the previous conditions remains the same. That means they must be a relation, and the relation must be a function. And since they are a function, then the same change, there is a small change. It is that in case of range, it is the list of all the second members of the ordered pair. The range in the above example is capital A, B, and C. Now you can see it here. Now to sum up the whole thing, domain is basically the first member of the ordered pairs in a function. That means small a, small b, small c, and the range is the second member of the ordered pair. That means capital A, capital B, and capital C. Let's talk about the function mapping now. Now when each element of the first set, called as the domain, is paired with exactly one element of the second set, called as the codomain, we call this whole process as mapping. In case of function mapping, what happens is that we do have two sets. The first set is called as the domain, and the second set is called as the codomain. Now when every element of the first set is paired with one element of the second, we call this process as mapping. If a function, let's check an example. If a function f maps a, b, and c onto capital A, B, C, and D, then we can say that the mapping process moves somewhat like small a is mapped to capital A, which is read as A is mapped onto A, B is mapped onto B, that means small b is mapped onto capital B, and C is mapped onto capital C. Then the domain is A, B, and C, that means small a, small b, and small c, and the codomain is capital A, capital B, and capital C. In this regard, we can say that if you would have seen previously, that means in case of domain as well as in case of range, we used to call the first elements, the pair of all the first elements, as the domain, right? And the pair of all the second elements, that means the y values, as the range. Here, while mapping, what we are basically doing is we are mapping the domains with the range. Now here, gradually what we are doing is we are saying that small a is mapped to capital A, as we have seen in case of small b, as we have seen in case of small c. Then the domain, we have said that it is A, B, and C, and the codomain is A, B, C, and D. Now in this case, you could have asked me a question like, irrespective of the status of the D, where is this D going? Now the condition of the D is that we are not mentioning anything about D here. Why? We are going to talk about this now. Now each element of the codomain that is mapped to the element of the domain is called as the image. Now the moment when we are mapping one element each of the domain to the codomain, those elements which are involved in case of domain as well as in case of codomain, then the elements of the codomain are called as image. Let us make it much more simpler. I am having the first set of elements as A and the second set of elements as B. A is having small a, small b, small c, and B is having capital A, capital B, capital C, and capital D. So small a is mapped to capital A, and small b is mapped to capital B, and small c is mapped to capital C, and D is remaining vacant. Now in this case, we can say that every element of the codomain, that means the B set, is called as an image of the first set, that means the set A. That means in this case, A, B, and C is the image, whereas D is not the image. Now each element of the codomain that is mapped to the element of the domain is called as an image. So from the last example, what we can see here, since A is mapped to capital A, B is mapped to capital B, and C is mapped to capital C, and D is left vacant, then we can easily say that the image A is the image of capital A is the image of small a. Likewise, we can also say that capital B is the image of small b, and capital C is the image of small c, right? So we can say that the image points for our last example is capital A, capital B, and capital C. Image points. Let's say during your examination, somebody can ask you that you're given two sets. You are given two sets, small a, small b, small c until n, and capital A, capital B, capital C until m. Then and the mapping sequences are shown. Then somebody can ask you what are the image points. Then you have to say all those parts of the codomain that are mapped to the domain. They are all called as the image of the domain part. Now, as they are mapped to the elements of the domain, it is called as the range. You can easily see from our previous examples, if you go back, in case of range, it is nothing but it is the list of all the set of members of the ordered pair. All the list of all the second members of the ordered pairs. Now, in this case, the range was capital A, capital B, and capital C. The same thing we're going to see here in case of image. That means in case of image, we can say that the range is nothing but the image of the domain part that is present in the codomain, right? In this case, D is not the image point, hence D is not in the range also. But D is definitely a part of the whole set, the whole codomain set. Thus, the range is the subset of the codomain. That means D will be included in the codomain, but it will not be there in case of range, and it will also not be there in another thing. What is that another thing? D is not a part of the image also. That means other than D, rest all things are an image of the domain part. Domain part is what? Small a, small b, and small c. And the codomain part is capital A, capital B, capital C, and capital D also. Out of which A, B, and C, that means capital A, capital B, capital C, are the codomains, and they are image also, and they are a subpart of the codomain. That means capital A, capital B, capital C, and capital D. There is one more thing that is to be noted out here, is that the onto mappings. What is an onto mapping? When set A is mapped to set B, and each element of set B is an image of the element in set A, then we call it as onto mappings. Thus, every function maps its domain onto its range. In case of onto mapping, let's see it in a much more simpler manner. Let's say I am having a set A comprising of small a, small b, small c, and set B comprising of capital A, capital B, capital C, and capital D. If we are having a set B in which all the elements of set B are mapped to the set A, then we call it as an onto mapping. That means there are no elements that are left behind in set B that can not be mapped to all the elements of set A. In another way, much more technically, we can say that all the elements of the codomain must be mapped to all the elements of the domain. If there are no elements of the codomain left up which is not mapped to the domain part, we call it as onto mapping. In this regard, there can be some of the questions that can be asked, like can we say in this regard that the range that is there is somewhat a subset of the codomain. In this part, in this case, we can say that the whole part is the same set itself. That means the codomain as well as the range remains the same, and the image is also the same. Why? Because in case of onto mappings, there are no elements in the codomain that is left unused or that is not been mapped. Okay, this is one of the lecture sequences. Let's see what is coming up next, and we'll simply be following the schedule. Thank you so much.